rather than Liz, let me welcome you all to this really, really joyous location. It's so nice that we can all be together for it, which is really neat. This is the culmination of how many? 7 years of Liz being here. And this is the inevitable conclusion of just a tremendous, tremendous history here of contributions to not only academia, but socially, in every way. Liz has just been a remarkable participant in our program. Liz came here from the University of Washington with a bachelor's in oceanography, a BSc in oceanography. She worked for a couple of years for CNC Technologies in Seattle. Yep. In Seattle, and then saw the light and realized that academia was the way to go.
Saw the multi-beam course.
So, there you go. That's even better. And started in 2015 with in a master's program, and went through that in a really wonderful effort to some pioneering work looking at broadband sonars and their ability to look at bubble plumes, methane bubble plumes, and try to be quantitative about it, really taking things a step above our ability just to see those plumes. And we certainly didn't want Liz to go, and she certainly had the wherewithal to do a PhD, so we transitioned her quickly into a PhD, which you'll hear about now, which you'll see. I think it's just as exciting and even more groundbreaking. And I think it's a really wonderful, and I give credit to Tom here, a real wonderful example of an evolution of somebody who came trained as an oceanographer, really quite general oceanographer from Russian. And as you'll see, has really kind of picked up the quantitative skills, really taking a nice theoretical look at some of the problems we face. But Liz, as I said, she was also a wonderful citizen of our community, was very involved with SHARP, involved with URGE. Now see if I can remember what that is. Unlearning racism in the Earth, in the geosciences, and that led a pod that I think was really one of the most successful pods, and actually created some software that's been used now. So all kinds of wonderful contributions. It's teaching. She's been teaching undergraduates. Actually, this morning taught. How's that for teach in the morning? Thesis defense a little later. All that time while raising 2 puppies and a husband. and has done a wonderful job with all of them. And so I'm just so proud of Liz. We all are. And the way this will work is Liz will make a presentation on the order of 40 minutes, something like that. We'll then open it up to questions from both the committee and the public. Anybody has questions? For those of you, I should say there are at least 50 people or so out there. So what's the number? 49. 49. That's close enough to 50 for geologists. Out there, for those of you out there, we're going to keep your microphones muted just to make sure there's no background noise. But if you have a question, you can put it in my chat, and Chris will interpret it. And if you think it's a good question, we'll ask it.
No pressure.
No pressure. But we'll have questions for about 30 minutes or so, I think, between the committee. Then we'll ask the public to leave. The committee will stay, and then we'll have a little more discussion with this. And then finally, deliberation. I should introduce the committee, but I also should say that another unique and pioneering thing that this has done is that she's actually getting 2 PhDs. One's not just good enough. 2 of them, one here and one at the University of Stockholm at the same time. This is another kind of groundbreaking program in Sweden. They do that every once in a while. It's new to UNH. We call it co-to-tell. Fancy word. And I think that we did a lot of arm twisting with the university. They agreed to it. And I think now they said they won't do it again.
No, there are multiples now.
Oh, okay, because I was told at one point, all right, we'll do this, but never again. I think they see the success of this.
See the light.
Yeah, and so the committee is myself and Tom Weber as the co-advisors, Martin Jakobsen, who's sitting in Stockholm, and Christian Strand, who's in Stockholm, Tracy Mandel, and Andoni. Is Andoni with us? She's here. Thank you. Good. Okay. Andoni, we wanted to get started, but I was going to keep going here until you got here, so we wouldn't miss anything in terms of the presentation. So thank you, Andoni at Woods Hole. So that's the committee. It's a big committee, but it's an interesting one. And Martin and Christian will be the co-advisors of the Stockholm PhD. So it's really, really interesting way to go. All right, Liz, I'll turn it over to you and then we'll have questions when we're done.
Okay, thanks, Larry, for that introduction. Hadn't thought about the fact that I was raising a husband as well. I just wanted to start by echoing Larry's sentiment that I just feel very happy to be able to be with you all here today. The video classroom, like Larry said, I got my master's here. So back in 2018, I defended here, and then the pandemic happened and it really didn't feel like we'd ever be able to be back together in this room. I actually defended my PhD proposal in December 2020, and I sat upstairs at my desk, and I think I might have been the only person in the building at the time. Mike Tuttle might have been here, making sure that the mice weren't taking over. And certainly I was happy to do that, but I feel very privileged to be here with all of you in person. And then of course, the ability to broadcast, because as Larry said, 3 of my committee members, so half of my committee are virtual. And there are friends and family, colleagues that I saw coming into the room. So hi everyone virtually. Like Larry said, my name is Elizabeth Reed Weidner, and the title of my dissertation is The Layer That Didn't Swim Away, Broadband Acoustic Characterization of Ocean Stratification Structure. So I'm going to start with some context for you all. I'm going to define ocean stratification structure, and I'm going to tell you a little bit about why it's important to the field of oceanography, particularly in our current moment. And I'll talk a little bit about what's missing in terms of our knowledge about stratification structure. And that will bring me directly to the sort of overarching goal of my work, which is the development of broadband acoustic methods to study ocean structure. This is really broken down then into 3 objectives. This is 3 different projects, and I'll take you through the highlights of those projects. And this will sort of be the bulk of the presentation. And then I'm going to wrap up by considering contributions of my work, applications of my research, really back to sort of filling in these holes in what we would like to know about stratification structure. So starting with the ocean, starting broadly. So if you're standing on a beach, on a dock, you're looking out to the horizon, you're seeing likely this sort of expanse of blue sameness. And that might give you the impression that the ocean, the water column, is relatively homogeneous, but it really is not at all. It is generally consisting of a series of increasingly dense layers. And we actually use the vertical density structure of the ocean to quantify stratification. So I'm going to be talking about stratification interfaces for the next 40-ish minutes. And these are regions of transition between these layers where properties like temperature and salinity are driving increases in density. And we quantify the strength of stratification or the intensity of stratification by the gradient of density with depth. So this is a stronger stratification interface than this one. Now, stratification structure doesn't all look like this. It's very much variable across the world's oceans. And that's because the structure of the ocean is really a function of a lot of complex interplay between other forcings. So globally, ocean structure tends to be defined by a balance between solar radiation, precipitation, evaporation, and then really large scale circulation. But then if you're in an individual basin, if you're in a small area, you really have to consider all sorts of other processes, such as ice formation and melt, different types of freshwater inputs, rivers, groundwater, meltwater from glaciers. You have to consider the effect of tides, the effect of prevailing winds, storm events, and then you have to consider mixing in the ocean. And that comes from, propagation of internal waves, effective currents, shear at layers, and at the molecular level diffusion. And so this can give you a sense that stratification structure can be hugely variable depending on where you are. So as an example, if you're in a high latitude fjord, you might have a very fresh meltwater layer right at the surface, the air-sea interface, and then really quite deep salinity driven structure or a halocline down at the bottom. Now in the open ocean, you might instead have the base of a mixed layer, which varies with the seasons, as well as a seasonal thermocline which expands and contracts, and then a deeper thermocline beneath that. And so in all cases, when we think about stratification structure, one of the reasons it's so important is that it modulates vertical transport in the ocean. So if you think about 2 stable water masses, the amount of mixing between them or any kind of exchange is going to be a function, at least partially, of the strength of stratification between them. So if you have a stronger interface, it's going to act as a bigger barrier to mixing between those water masses. And so as a result, stratification structure modulates vertical transport, and it's affecting all sorts of different processes, including the ones I have here. So for example, the ability of the ocean to uptake both heat and carbon from the atmosphere, the distribution of heat across the ocean, long-term ocean ventilation, lots of different biogeochemical processes that are linked to the cycling of nutrients and the availability of nutrients, and then primary productivity rates in the photic zone. And ocean structure, and partially because of all of these forces, is particularly in focus right now because our human-induced climate change is altering ocean structure, particularly upper ocean. So this is the figure of a number of oceans, the Southern, Pacific, Indian, Atlantic, showing the change in stratification intensity just in the last 60 years. And that's not a very long time scale for our oceans. And you can see in the upper 100, 200 meters, we have these red colors, and that's an indication that stratification is becoming more intense. Those gradients are becoming stronger. And these trends are expected to continue. And as you can imagine, those changes are affecting all of these processes. So there really is a strong need in the oceanography community, in a number of communities, to be able to quantify stratification structure interfaces, specifically where their position is and what their intensity is. You might be working in the open ocean. You might care about the strength of the mixed layer to get at your seasonal rates of primary productivity, or you're working in a high latitude fjord and you want to measure the thickness of this layer in order to estimate mass loss from glaciers. Either way, you really need to get at rapid synoptic and high resolution observations of ocean structure, and traditional methods might not provide us with what we're looking for there. And that brings us to acoustics. So acoustic systems provide us with a near synoptic view of the water column. And they provide high resolution data, not only vertically, but also spatially, because sound moves very fast in water. So you can collect acoustic profiles really rapidly. And as you can see from just these figures, for the last few decades, really actually maybe more than a few decades, 1975, acoustical oceanographers have been observing scattering that's associated with ocean structure in the world's oceans and working towards quantifying it as well. So not necessarily a new idea to use active acoustics to study structure. What is new is the commercialization of broadband acoustic systems. So broadband systems send out a very specific kind of acoustic pulse which sweeps over a range of frequencies, given the name. And with some signal processing, broadband acoustics provides both high signal to noise ratios and really fine scale range resolution. And that allows for discrimination or identification of really closely spaced weakly scattering phenomenon, such as fine scale ocean structure. These are thermohaline staircases. You can tell that because they look like a staircase. They're individual stratification interfaces made up of very small changes, noting these scales of temperature and salinity. And we can observe them in the broadband acoustic echogram as a series of very thin scattering layers. Now, the ability to discriminate fine scale structure is great. Broadband acoustics also provides us with frequency modulated scattering information. So that allows us to better characterize the scattering from some kind of phenomenon in the ocean as a function of frequency. How does it scatter sound? And we can discriminate between different types of scattering phenomenon with this data. So this brings us to my work. My goal of my PhD was really broadly the development of broadband acoustic methods to study ocean stratification structure with these commercial pieces of equipment, leveraging the rapid and synoptic abilities of active acoustic systems to observe ocean structure in the water column and provide very high resolution measurements, both spatially and vertically, of ocean stratification structure beyond what you would be able to do with traditional sort of direct sampling methods. And all that time working towards being able to acoustically measure through inversion of our data metrics of stratification structure, such as its position and its intensity. So this goal was, I hope you'll agree, generally met through a series of objectives, and I'm going to take you through them one by one, starting with the first, the development of acoustic methods to map out the spatial temporal extent of stratification structure. And for that, I'll take you to the Baltic. It's a marginal sea, so this is the Baltic, of the Atlantic Ocean. So the Atlantic is sort of off the screen over here. It's a region that many of its basins are known for not only strong stratification structure, but also low oxygen conditions, as you can see from these news clippings. That causes all sorts of issues for Baltic states, both environmentally, economically. And we worked in Western Gotland Basin, which is a region that is known for not only permanent low oxygen conditions in the bottom waters, but that oxygen is linked to very strong stratification structure. So we collected data on RV Electra using a broadband system sweeping from 45 to 90 kilohertz along all these track lines. The positions here are the positions of direct sampling of the water column using a CTD probe. And wherever we were, we observed in the water column this very thin horizontal scattering interface. It ranged between depths of about 50 to 70 meters. You see here it's at 60 meters. And this agrees with the general position of the stratification interface in the literature. So in order to sort of pull apart what is causing scattering here, is it stratification structure, and then work towards tracking if that in fact was the case, we looked at these co-located data sets where we have both calibrated and corrected acoustic data, water column data, and we also have direct measurements of the water column. So you can see this is the CTD probe actually going down and coming up in the echogram. And so what we see in our direct measurements are two very, very strong stratification interfaces, and they're at the same position roughly as our thin scattering interfaces that we see in the acoustic data. So in order to directly compare these data sets, we computed the plane wave reflection coefficient. This is a measure of impedance. It's a measure of the medium. So when medium properties change rapidly, we expect to see a large value here. In order to extract this value from the acoustic data, I used a simple acoustic scattering model defined in Strane et al. It actually was used in that paper with the thermohaline staircases you saw earlier. And it says that the scattering that we're observing, so the colors that we see here, is going to be estimated by the reflection coefficient plus the area insonified. So what we're saying here is that our stratification is actually a surface that extends beyond the area of our insonified beam, and that area is going to grow as we look deeper in the water column. So we can invert this for this reflection coefficient model. The CTD, we can actually just measure those properties directly. And the result are these two peaks in our reflection coefficient where we have changes in oceanographic properties. And you can see we have excellent agreement both in the position of the peaks, but also in their magnitude, which tells us two things. One, we can, using our acoustic data and this model, track this primary stratification interface by pulling this peak reflection coefficient. And two, what we're observing here in terms of scattering is likely due, at least primarily, to the oceanographic properties, the change of that from the stratification structure. We also, it turns out, can track the onset of low oxygen conditions. So here we have the oxygen profile, fully oxygenated in the upper water column, and down here, no oxygen whatsoever. And the onset of that decline is coincident with the peak reflection coefficient. So in tracking that, we can also track this gradient of oxygen. And we saw these trends, not just at the one CTD that I'm showing you. I'm not showing you the one good case. We saw these trends across the survey regions. We have good agreement between the peaks and the magnitude, tracking the structure itself, but also tracking this decline, specifically a level of 2 milliliters per oxygen per liter, which is the hypoxic horizon. So in order to actually track this interface, we developed a tracking procedure starting with that reflection coefficient profile. And then there was a step where we filtered those profiles using split aperture and some other processing. And from that filtered profile, we picked this peak reflection coefficient. That data set was then spatially filtered along track. And from that, we extracted latitude, longitude, and depth. So as an example, here we have an acoustic transect, right? We're collecting some direct measurements of our water column here. Then we start to transit. We have about 10 to 12 kilometers of transit here. Applying the procedure, we can track this primary interface for the entire transect. And this track is very highly resolved spatially, about 3 to 5 meters of resolution, vertically closer to 5 centimeters of resolution. And so having tracked that over the whole region can create a map by interpolating between our measured depths, so between our individual lines, using a natural neighbor function on a defined grid, 500 by 500 meter grid around this general region. Any region that was less than 50 meters in depth was masked because we never saw the interface shallower than that. And this is the result. So this is the depth of this primary stratification interface and also the onset of the anoxic zone across Western Gotland Basin. And of course, if you wanted, you could create a map from your individual discrete stations, right? There's about 20 of them. But clearly, the acoustic data provides a lot more resolution in terms of the spatial distribution, the detail of this interface. And it was very easy to collect, and it was fast, right? We let the acoustic systems run as we transited between our CTD stations. And so we are showing here that broadband acoustic data, or actually just acoustic data in general, can provide us with really high resolution measurements of these interfaces spatially. So So now the clicker isn't working. So there we go. So the goal of objective 1 was met by basically leveraging the fine range resolution and the high signal to noise ratio of our broadband systems and utilizing a simple acoustic scattering model to identify this position of the stratification interface. We actually tracked it using acoustic inversion, and we verified at ground truth stations. So the existence of the ground truth data is important, right, in this method. And what I showed you on the previous slide is the result, a map of the stratification interface at a much higher resolution than we could have achieved with traditional methods alone. So hopefully we all agree, check box by objective 1. However, when you're doing research, of course, lots of questions come up. And one question that kept coming up, mostly from Tom, was why is it that we observe scattering from an interface that's defined by a smooth gradient, right? Because stratification structure is a gradient between two water masses. And our acoustic scattering model certainly does a good job of tracking this interface, but it does not explain why we are observing scattering. So the next objective was to define a scattering model for ocean stratification interfaces that utilize this idea that stratification is a smooth gradient. So first thing to do is to really define the physical system. So here we are defining a region of stratification structure as a smooth gradient between two bodies of water. What that means mathematically is that it's a range-dependent perturbation in both density and bulk modulus away from the background values, right? So it's changing. We state that these values are small with respect to background values, and that our region of stratification structure obviously can have different vertical length scales, right? And that will control how intense it is. If L is small, then this change is happening rapidly, but it can be very extended. We also assume that this region is far from our acoustic transceiver and receiver, and it only is really varying in one direction. And this allows us to define a one-dimensional acoustic scattering model. First part of that is to define the wave equation. So this is the one-dimensional reduced force wave equation, which explains the behavior of scattered pressure from a medium that has perturbations in it. The medium for us is the ocean, and the perturbations come from this stratification structure. So on the right side of this model are two forcing terms. They're sources of scattered sound due to the interaction between our incident pressure wave and the stratification structure. So if there is no structure, this side of the equation goes to 0. The first term is delta K squared. That's the acoustic wave number perturbation, and it's a function of both of these perturbations. Both density and bulk modulus are in this term. The second term is only a function of the density perturbation, and it's the density perturbation gradient term, which is a nice big mouthful. So having defined the acoustic wave equation, now we want to define an equation for our scattered pressure or total pressure that satisfies this model. And we did so with a Green's function solution. So here, just showing you the scattered pressure, which is an integral over dr prime. Dr prime being the region where these perturbation terms are non-zero, so where we have structure, basically. And what this model really says is we're going to take those two forcing terms and we're going to multiply them by the one-dimensional Green's function per propagation. And we're going to integrate over the range of our source, which is our stratification structure. You'll note in here, we have incident pressure. So for those of you in the acoustics field, we are making the Born approximation. We are assuming we are working with a weakly scattering medium. That's one of our initial assumptions. And so we can just put incident pressure into our integral here. Having defined our expression for scattered pressure, one of the questions is, certainly both of these terms fall out of the math, they fall out of the physics, but how important are they in comparison to each other? Do we need to consider both terms when computing pressure? So we looked at the relative importance of these terms at 5 different test cases from the literature of ocean stratification structure. So 2 you've already seen, thermohaline staircases in the Arctic, our interfaces in the Baltic, which actually also are thermohaline staircases, by the way, thermohaline staircases in the tropic, the base of the mixed layer in the Arctic, and a glacial meltwater lens. And the results of that analysis tell us that we can actually remove entirely this second term. The magnitude of that term when it comes to the scattered pressure is so much smaller than our wave number perturbation term, we don't need to consider it. The other thing that we did to simplify was change the geometry to just backscattering geometry, because that's the kind of data that we're working with. And so this is the result. This is our final expression for scattered pressure. It's still an integral over our region of perturbation, but now what we have is delta K. This is our wave number. This is our wave number disturbance. and it's being multiplied by this complex exponential and P naught. P naught is just a number, it's just the amplitude of our incident pressure wave, it's frequency dependent, and this whole integral looks like a spatial Fourier transform of our delta K perturbation at a half wavelength scale, because there's a 2 there. So this is a model that we can apply to ocean stratification interfaces, but it will break down where the density gradient term is important, where we have interaction between fresh and salt water. So this is that glacial meltwater layer. At that location, at low frequencies below 5 kilohertz, the density gradient term starts to sort of creep up into importance. And so there you want to make sure you put that back in there, so you can't use this model. This is a note in case anyone, Jamie.
Just a quick clarification. Are your wavelengths bigger or smaller than
Well,
this?
we're gonna get to that, aren't we? So, forward problem. We've defined our model, and what we'd really like to do is look at the behavior of the scattered pressure. We'd like to be able to see if what comes out of the model predictions matches what we've acoustically observed in the field at these interfaces. So we picked a sound speed profile to evaluate this delta K term. And we use the one actually from this location of thermohaline staircases. So we have staircases here. We also have a stratification structure and interface at the base of the mixed layer. This model was numerically integrated with 2 complex sinusoids, one at 2 kilohertz, one at 20. And the outputs are scatter pressures relatively low. This is a weakly scattering phenomenon, so that's good because that's our initial assumption. And what we can see is that, first off, the mixed layer, strongest reflection in the model, significantly stronger at 2 kilohertz than it is at 20. So that suggests right away that there's something frequency dependent about the scattering from the structure, which is sort of what Jamie just asked, but we're going to get there. The other thing to note is the region of thermohaline staircases at 20 kilohertz. For every individual staircase step, we see a discrete reflection peak associated with that step. So we have behavior that agrees with what was happening in the field, right? We were identifying those individual thermohaline staircases as interfaces. We were seeing them as discrete steps at about 18 kilohertz. So to tease out that frequency dependence, we, instead of a forward problem, defined an inverse problem where we define a functional form or an analytical expression for delta K, and we plug that in. So we chose a single thermohaline step, and we said, all right, we can approximate its range-dependent shape as 2-layer stratification. So we can use inverse tangent to describe that shape. And one thing about inverse tangent, which we're going to care about, which is hugely important for this objective and the next, is this parameter A. And this is the sharpness of the interface. So as A becomes large, right, as A goes to infinity, this step becomes actually a step, a discontinuity. So it defines how rapidly we're transitioning from one layer to another. So take this expression, plug it in, you can solve the integral, and you get this expression for scattered pressure for stratification structure that looks like inverse tangent. You have a frequency dependent incident pressure, right? You have this sound speed term, which looks like our plane wave reflection coefficient, except without the density in it. So the density gradient being ignored here, but otherwise our idealized reflection coefficient or a good approximation of it. And then 2 exponential terms, both decaying. One is a delay term that just places the interface, the scattering from the interface where the interface position is. And the 4th term in this expression is the one that we really care about. This defines a relationship between A, the sharpness of the interface, and K, which is the acoustic wave number. Frequency is buried in that. So we're defining a relationship between the frequency with which we insanify this interface and the sharpness. So we can rearrange this expression to create our own pressure reflection coefficient. And what we end up with is our sound speed term being modified by a term that exponentially decays. So this defines the frequency dependent behavior that we might expect to see from a stratification interface. So we define A, we say, all right, this is the sharpness of this interface. If this exponential is close to 0, this whole term goes to 1. And all we have left is our sound speed term. That defines the maximum scattered pressure level that we could possibly have from this interface. When does that happen? That happens when we have really, really low frequencies, when the length of the wavelength is significantly longer than the interface itself. So I hope that answers your question, Jamie. Yep. As frequency then increases, this term gets bigger, the whole term decreases from 1, and we lose energy. The slope of that line is defined by this term. It's defined by the sharpness of the interface. So in theory, if we had enough broadband frequency content, we could not match that slope and predict A. from the data, from the acoustic data alone. So objective 2, goals for objective 2. We did define a one-dimensional model for ocean stratification structure using this sort of idea of them being smooth interfaces. We did make some simplifications based on stratification structure in the ocean and also the geometry. We evaluated then that final model with forward and inverse methods for some known stratification interfaces. And from those inverse methods, we were able to derive this analytical relationship between interface sharpness, or its thickness, its vertical extent, and the frequency of insonification. So obviously, in terms of follow-up, we would like to apply that model, right? We'd like to see if we can extract those values. A couple things that have to happen. First, we need to expand our one-dimensional model to consider a surface, because this is an echo sounding application. We're going to insonify an area. And if that surface has roughness, what will that do to our frequency dependence? Will that modify the frequency dependence we've already predicted? So that's the goal of objective 3, expand and apply our scattering model to characterize the broadband acoustic response of a rough stratification interface, actually a series of increasingly rough stratification interfaces. So first step is to expand the model. There is lots of literature in underwater acoustics for scattering from rough surfaces. Seafloor, sea surface have all been modeled that way. So lots of literature to pull upon. We use the Helmholtz-Kirchhoff integral, which allows us to compute scattering from a surface. This says that the complex pressure at some field point, which for us is our receiver where we're listening, is going to be a function of the wave field on the surface. So you're going to integrate over the surface, individual elements of that surface. We made the Kirchhoff approximation, which lots of people do in the literature. We say that for this approximation, the scattered pressure from the surface is only going to be a function of the incidence pressure, so whatever that pressure is, its amplitude, and then the reflection coefficient. That's defined by the surface itself. This approximation places some limits on us. We can only work with surfaces that are smooth enough that we're not going to have any acoustic shadowing. We're not going to have any multiple scattering effects. So I'll talk about that in a moment. And then we also simplified for a whole mounted geometry. We don't have a separate source receiver, so that picture becomes simpler. And this is our expanded acoustic scattering model that considers a surface. You'll note R prime, that's our modified reflection coefficient, which says that the frequency dependence of the scattering is going to be a function of A and your frequency, and it's buried in there. The real question then is, what does this do to the frequency dependent scattering? Does that affect it, or can we just utilize this? So surface generation. We defined R prime using a sound speed perturbation of 1.2 meters per second. So as a reminder, that's going to just shift this up and down, right? We define the sharpness of the interface A as 1,490. That defines this slope and is equivalent to a thickness, the vertical extent of an interface, of about 3.5 centimeters. The surface itself is a statistically rough surface, Gaussian distributed roughness, dependent on the root mean squared height of the surface, which controls the magnitude of the roughness vertically, and then the correlation length, which controls the spatial distribution of roughness elements. So root mean squared heights from smooth to acoustically resolvable, correlation lengths, the length of an acoustic wavelength, particularly at 45 kilohertz, up to much larger than the beam footprint. Now, all surfaces defined with any combination of these factors falls within the limits of the validity for the Kirchhoff approximation, both the traditional sort of optics, I believe, limit of the Kirchhoff criterion, but also the correlation length limit set by Thorsos in 1988. So we have defined our parameters. How do we evaluate the model? So we're going to evaluate the model for our complex pressure. And we do this by defining a specific distribution of roughness. And then we define 50 independent realizations of surfaces, and we evaluate the model for those. The model was evaluated at 13 meters depth for a frequency range of 45 to 270 kilohertz for a piston transducer beam pattern. And the output are then 50 independent measures of complex pressure from surfaces that have the same statistics, roughness statistics. So model results, lots of them. 66 total simulations that were defined by both our root mean squared height and our correlation length. From those 50 scattered pressures, we took a number of averagings. We computed the total scattered field, it's plotted here in green and also on here in green. And I realized this morning that it's really hard to see green. I apologize for that. And then the coherent field, which is plotted in black, plotted here in black. And you'll note as well, there's a red line on all of these. This is the scattering from a perfectly smooth surface. This is from the image source solution, and that's the expression for it. you'll note that it doesn't change, right? There is no roughness on the image source for the image source solution. So its frequency dependence is only a function of our modified reflection coefficient. It's just a function of the stratification intensity. Before I get into model results, I just want to talk briefly about how scattering is affected by roughness on a surface. And then I'll talk a little bit about the nature of behavior of both the coherent and the total field. So when we think about roughness and increasing roughness, how is that changing the scattered pressure from the surface, right? Because this is a model where we're integrating the scattered pressures across that surface to get at the total scattered pressure at our source receiver. So there's two things. There's the magnitude of that pressure and there's the phase. The magnitude is defined by the similarity in the direction the surface is tilting. So its normal component to the backscatter direction. So when these vectors are the same, you're at the peak magnitude, or when psi is 0. The phase, on the other hand, is connected to the length between the surface and the receiver, so the magnitude of RS. So if we have a perfectly smooth surface, our backscattered field is going to be dominated by energy from the center where phi is 0. This is called the specular return. This surface is effectively acting like a mirror to us. And the phase of a perfectly smooth surface is going to be defined by these regions of equal phase, and the changeover from positive pi to negative pi is the limit of a Fresnel zone. If you're an acoustics person, that's what that's called. And so as we make the surface more rough, we distort both the backscattered field and the phase, because we take those individual surface elements and we start to tilt them away from being smooth. And they become increasingly tilted as the roughness increases. We also modulate the phase because we introduce vertical path length differences, the magnitude defined by the amount of roughness, which introduce phase offsets. So the result is a backscattered field that goes from being defined by the coherent to being defined by individual element roughness across the surface. The phase, those individual Fresnel zones become increasingly distorted until actually the phase across the surface is totally random. So now let's talk about behavior. First, we're going to talk about the coherent field. This is a measure of the in-phase energy. So it's at a maximum when we have that perfectly smooth surface. That's totally coherent. And the loss of the coherent field is a function of the root mean squared height of our distribution. So fortunately, I'm not going to make you look at that giant figure the whole time. So here we have increasing root mean squared height as we're going down. And I'm plotting all of the model simulations, or all the correlation like model simulations. So we have every model simulation at this root mean squared height. And what we can see immediately is that there is a frequency dependence to loss. As we increase frequency, we have an increased loss in the coherent field. And as we increase our RMS height, we have an increased loss in the coherent field. So what's happening here? Well, the loss of coherent energy is directly linked to the vertical path length differences. And the magnitude of those random path length differences is linked to the RMS height, right? It controls the vertical distribution of heights on the surface. As you introduce these vertical path length differences, you increasingly randomize the phase of the total field at the receiver. And as a result, if you randomize phase, you're going to lose in-phase energy. So as we increase RMS height, the in-phase energy goes down and the coherent field is reduced. And this is very, very strongly frequency dependent, because for a given path length difference, for a given RMS height, that length is going to be a significantly larger portion of a wavelength at high frequencies, which have short wavelengths, versus low frequencies, which have long wavelengths. And we can actually quantify the mean surface roughness with respect to wavelength using the Rayleigh roughness parameter and evaluate that. And we can use this parameter to define the ensemble average coherent loss of the field, which is plotted here in the dotted line. We're seeing that it predicts the overall loss of energy as we increase our RMS height and over frequency. And the Rayleigh roughness parameter is evaluated for mean surface statistics, not for individual surface statistics. So the takeaway here is that if we could measure the coherent field over a large enough range of frequencies, we could actually invert for the RMS height distribution of the surface using the Rayleigh roughness parameter as our model. So now, I'm taking a drink. I'm going to switch over to the total scattered field. So this is an ensemble average of the magnitude of the scattered pressures, no longer considering phase, which means we have both the coherent and the scattered fields in this term. And its frequency dependence is a function of both the root mean squared height of the distribution and the correlation length. And we quantify this by the root mean squared surface slope angle, or gamma. And this really is just a measure of the distribution of individual surface elements tilts away from smooth. So a perfectly smooth surface has a gamma of 0. So gamma is increasing from the top left to the bottom right. And we can use gamma to define a number of different behavioral regimes. So first, we're going to focus on these two regimes when RMS heights are low and when gamma is small. And in these cases, our total field is effectively indistinguishable from the image source solution. In other words, the scattering from these sources in an ensemble average sense can be modeled in the same way you would model a smooth surface. So why is this happening? Well, when RMS heights are low, the total field is also effectively indistinguishable from the coherent field, meaning that it's totally coherent. We already talked about loss of coherent energy. We know as we increase RMS height, we introduce these vertical path length differences, and that creates phase offsets. But if RMS height is significantly smaller than a wavelength, then those phase offsets that are being introduced are negligible. We can't measure them. So what's happening on this side is that we have surfaces that are smooth at the scale of our observation. Now, if we move over that line, that's no longer the case, right? RMS heights are taller. So what happens when gamma is small? How is gamma small? Well, even if you have really, really large RMS height, if you take that and you distribute it over really, really long lengths, your overall tilt of individual surface elements is going to be small. And in these cases, the backscattered field, although distorted, still is effectively dominated by energy from that specular return. And if you take a lot of ensemble averages, the overall magnitude of the total field is still going to be very similar to the image source solution. So the big conclusion here is that there is a huge number of model simulations in which the spectral slope, the frequency dependence, is still just defined by the modified reflection coefficient. These surfaces can be modeled as if they are smooth, even though they are not. And that means that surface roughness isn't coming into play here. We do need to delineate this regime, both of them. And so that was done by defining a threshold value, no more than 2 dB of RMS deviation over the whole bandwidth away from the image source solution. So that's how this limit was set. And that's set by really the kind of variability you expect to see in the field. If you have 2 dB of variability in your measurements, then you're doing a good job. But certainly that could be made more constrictive. So now we're going to switch over to the location. We're going to switch over to the location where our RMS slope angles are getting large, right? So our surfaces are getting very rough. And here, there are 2 things that start to happen. And I'm actually going to plot everything together just to give you a sense. I'm also going to take linear regressions of each of the examples of RMS slope angles. So we have 4 here. We have 4 different RMS slope angles that we're testing here. And what we can see overall is that as the surface becomes more sloped at its individual elements, we, one, have a loss in magnitude over the whole band, right? The whole band has less energy in it across our entire frequency bands. Also, if you look at the slope of these linear regressions, they actually are becoming a little bit more negative. So they're tilting downward just slightly. So we are losing more energy at higher frequencies. Certainly the dominant trend is this loss of energy with increasing RMS slope angle. So what is happening here? Well, I already sort of told you, but as we get very rough, the backscattered field is dominated by individual surface element roughness. So as it becomes more rough, we actually scatter more and more sound away from the backscattered direction. So we have less energy to work with in total. And as the surface gets more rough, the phase becomes more randomized. So when we sum all of those scattered pressures over the area, you have deconstructive interference. That's linked to phase being strongly frequency dependent. So at higher frequencies, we're losing more energy faster than at low frequencies. Now, the limit of this regime is a little bit fuzzy, because really what you would be looking for is at what point would you not be able to observe scattering from this surface anymore. However, that's really linked to the signal to noise ratio of your system and where you are in the ocean. So, the point at which there's no energy left is sort of up for debate. I set a relatively loose limit of as long as the total field over more than half the band was above 125 dB, which means the high frequency half of the band, then it was observable. But certainly this should be updated depending on what system you're using. And so I want to end talking about the model simulations by defining some regimes and what kinds of measurements we could make from our acoustic data. So when we are in the regime of small RMS heights, small RMS slope, we can define the sharpness of our stratification interface directly from our spectral slope, because it is only defined by our modified reflection coefficient. So we can use this, we can match the slope, we can get A. When RMS slope angles are small, we should also be able to extract the RMS height of our distribution if we are able to measure the coherent energy, because we can use the Rayleigh roughness model parameter as our model. Now, in the region where RMS heights are small, we can't actually measure it directly, but we can set an upper limit to what that RMS height could be for a given frequency range. Sort of in a similar way, when RMS slopes are large, we could set a lower limit to the sharpness of our interface. And this is because the spectral slope is defined both by the modified reflection coefficient and by gamma. Now, if you knew what gamma was, you certainly could get A. If you don't have a measure of your interface roughness or that slope, you could say what the lower limit of A is as it's being modified. The slope is being modified to be more negative. And in this case, because our RMS heights tend to be much larger, we probably don't have enough coherent energy here to extract the RMS height directly from the data. But if there was coherent energy, if you were down here and the correlation lengths were short, you might be able to get at this parameter. And so I want to end objective 3 by talking about applying what we've learned about these regimes to 2 different field data cases and extracting interface sharpness, or at least constraining it. So first we'll be in Western Gotland. So we've been here before. We don't have any measurements of interface roughness here, right? We don't have those directly, but we do have a lot of information at our disposal. We know that double diffusion is creating thermohaline staircases in the water column here, which means there's not very much energy in this water column. Also, as we drift over this interface, it's effectively flat. It's not moving up and down at all. And this is actually a measure of interface coherence. This is split aperture coherence. So looking at the individual quadrants of our split beam system, whites are totally coherent, blacks not coherent. And you can actually pick out the interfaces because they are so coherent. So we expect with all of this information that this interface is sitting in this small RMS slope regime, or perhaps even very small RMS height regime, which means if we can measure the frequency dependent, calibrated, corrected scattering as a function of frequency, we should be able to match this slope, and it should be proportional to our modified reflection coefficient. So for this particular slope that's measured, A, our sharpness parameter, is 2800, which is connected to a delta Z of approximately 1.8 centimeters. If we then transition to the Kattegat basin, this is a remarkably different basin than the Baltic. They're very close together, but the Kattegat is very energetic. There are inflows of Baltic water here, there are prevailing winds, and even just looking at our interface, the stratification interface, we can see that it's a lot more dynamic, right? So there are short period internal waves propagating along this interface, and that is tilting the interface back and forth by about plus or minus 3 degrees. Which feasibly, I mean, not only is it tilted, could support smaller scale roughness on the interface. And the correlation, the split aperture correlation analysis, in very stark contrast to the Baltic, here's our interface, and here's the CF data set. There's no coherence here whatsoever. We can't even pick out the interface, right? We don't even know where it is in this data set. So not at all coherent. So feasibly, that could be because there's interface roughness, because the interface is being tilted, so we're not having any coherence. So if the scattering that we're observing here is due to stratification structure, then we're likely in this regime where our RMS slope angles are large. Now we are observing scattering, right? So we're not down here. So we're somewhere in here, which means if we measure the frequency dependent scattering, which has been calibrated and corrected, and we match that slope, we certainly still can match it to our modified reflection coefficient. But remember, likely roughness on this interface is forcing that slope lower. So we can only set a minimum value for A here. A might actually be larger than this value. So 1490, which is associated with a vertical extent of no smaller than 3.5 centimeters. So objective 3, hopefully check mark, hopefully you agree. I think the goals were met. We certainly did expand our acoustic scattering model using the Helmholtz-Kirchhoff integral, Kirchhoff approximation. We then applied that to a number of different interfaces, increasing roughness. Certainly they were constrained in their roughness by the Kirchhoff approximation. And from that, we defined these regimes of behavior where we could extract different types of parameters, or we constrained what we could extract. And then we evaluated potential acoustic inversions at a couple of different interfaces. Now, of course, I can imagine you can think of a lot of follow-up to this work. I certainly can. One thing would be that coherent field. It'd be great to get at the coherent field and try to extract an RMS height value for that distribution. But also probably it'd be great to test to see if that sharpness is in fact correct. We don't have any very high resolution measurements of that interface. We have CTDs, but they aren't high enough resolution to extract that kind of sharpness measurement. So that would be excellent to collect. And also because then we could evaluate other potential scattering mechanisms, particularly in the Kattegat. There's a lot of biology there. There's a lot going on. So it would be great to get some more direct information from that. And so I'm going to wrap up now by just talking a little bit about the general contributions of this work. I'll start with a reminder that ocean structure is changing. Human-based climate change is modifying particularly upper ocean structure. So there's this real need, and it's been noted in a number of papers, that we really need better information on stratification interfaces. Where are they? How are they changing? How's their intensity changing? And the goal of this work was to fill that need by developing these broadband acoustic methods to offer very rapid synoptic and high resolution measurements of stratification structure for measurement now and for monitoring into the future. And I do think that this was met. I think objective 1 showed us that acoustic systems can collect very high resolution data of an interface and track it over large distances very, very rapidly. And this high resolution data is a lot higher resolution than the traditional methods, both spatially, at least spatially. Clearly, I mean, we can see that from where the traditional measurements were made. Objective 2 really dove into why we observe scattering. And we were able to define a model that can be utilized as stratification interfaces, but also a model that predicted this relationship between the frequency of insonification and the stratification interface intensity. And of course, objective 3 then took that one step further to test out a number of rough surfaces and define these behavioral regimes in order to tell us what kinds of parameters we might be able to extract with acoustic data alone. Obviously, if you had measurements of your interface roughness, you could do more. And I wrapped that all up by applying these methods. I didn't tell you about this, but I did track this interface as well. There's just not enough time. But to apply these methods to both measure position and intensity, or at least constrain intensity in the case of the Kattegat, via broadband acoustic inversion. So I would say in conclusion that we did develop broadband acoustic methods to track position and at least constrain intensity of ocean stratification, both remotely, rapidly, and at high resolution spatially and vertically. And with that, I will wrap up. Before we take questions, I just have some acknowledgements to make, some that I need to make, and I want to. Of course, I want to acknowledge all of those institutions and groups and departments that provided me funding during my time here as a PhD. My academic homes, University of New Hampshire, Stockholm University. Didn't get to spend as much time at Stockholm University as I would have liked because of the pandemic, but still always felt at home there. And then of course, CCOM, my home away from home. A number of different foundations, groups provided funding for this research, either directly to me or to the PIs that I worked with. So of course, I'd like to acknowledge them as well as the departments here at UNH and Acoustical Society of America. There are lots of people who have to be thanked. And if your name isn't up here, that doesn't mean I'm not thanking you. I just couldn't put everybody's name up here. Committee members, obviously, Larry, Martin, Christian, Tom, Tracy, and Doni, thank you for your support of my career and your advice. In particular, Tom was my master's advisor, and I really appreciate that. He has always pushed me to be better. He's always pushed me to dig deeper into a data set. Why is it doing that? Do you really understand? Pull the thread, pull the thread. That's his favorite thing to say, pull the thread. And I think it really helps me become who I am today, and I'm very grateful. And Larry met me in December of 2014. I was in town, not related to being a student here, and I called him, and he was in the building at the time, and he gave me a tour, which I realize now is crazy that that was even possible. So he doesn't even remember, but that Larry would have been here when I called and would have had time to give me a tour. I believe he introduced me to Val at the time. And then of course that he took me on, and he's always given me wonderful advice, and he has great intuition for the work we're doing. I believe he was the one who looked at the Odin echogram at the base of the mix layer. I think it was the mix layer. And he was like, we're seeing scattering right where that interface is. And that started all of this. So I can only ever be thankful for Larry for his advice and his support. And then of course at CCOM, there are a number of individuals who made this possible. Chris should get a big thank you. He fixed the projector. It wasn't working this morning. He fixed Zoom. The whole Zoom server crashed and he fixed it somehow. But the whole IT team, Will and everyone, as well as the administrative staff, Wendy, and a number of people who are working here at the center, at UNH, the graduate school, and members of the Earth Science department. And then at SU, I didn't get to spend as much time there as I would have liked, but I always felt at home. Whenever I arrived, there was a big pile of apples and a giant jug of peanut butter sitting on my desk. So someone figured out that I liked that. And then of course, the captain and crew of the ships I worked on, the data that you saw here was collected on RV Sevilla and RV Electra. And then I was on Icebreaker Odin as well as a number of other ships during my time, but this was just a really amazing experience in Northern Greenland. So thank you to the captain and crew of those ships for making data collection possible, and the science parties, Christian Strane and Jonas Sundenberg, for their work on RV Electra when they brought me along. And then there are lots of people, individual people, friends and family, and my husband, Alex Padilla, who is here virtually from Woods Hole. If she hadn't been here, I would not have gotten this degree. Her and I started at the same time. Brandon and I actually started at the same time as well. And Sam, my husband, who has been so supportive, along with the rest of my family members, the Schmidt family, in the long nights and the months away at sea. And I just thank you all for all your support. And with that, I would be very happy to take your questions.
Thank you.
Thank you.
And I forgot to mention, hold on, Jim. I forgot to mention in the introduction that another thing Liz has done all these years is that almost every time she goes to a conference, she comes back with the best student paper award. I mean, we expected that. But I think with this presentation, you see why. It's such an ability to explain complex things in a very sensible way. I'm going to add one more acknowledgement because I saw him logged in. And this is not something that you probably recognize, but certainly Tom and I do. I saw Jeff Condiati logged in. And I think both Tom and I and the whole lab here owes a great deal of thanks to Jeff and Kongsberg for all the support they provided in terms of instruments and instrumentations. Jeff,
yes, and support. Yes, thank you, Jeff, if you're still there. Lars, Toringa. Yeah, wonderful.
Exactly. Okay, now, James.
So this is super cool. I can see like 100 different places it could go. One thing that struck me is you were in very quiet environments. How would you, if you had backscatter from unstratified turbulence, how would you say that's
yes? Yeah, so that's one of the big questions, which I just didn't fit into this presentation, but is that there is always ambiguity in acoustic data, at least initially when you're observing the echogram. What is causing scattering? And that's one of those big questions in the Kattegat, because it's very biologically active and obviously energetically active. And so when you have two layers together, you're going to have shear, and there absolutely is scattering, and it's actually there's stratified turbulence. Is a particular phenomenon which has been studied. Andoni's on the call. She's got some papers on that. So yes, I think differentiating the scattering, when are we seeing these smooth gradients versus when are we seeing the effects of shear and mixing between water masses is a big question. One way to potentially get at that is the frequency dependent scattering, because they're going to have different spectral slopes. The other way would be with your very high resolution direct measurements of the water column. And you could measure background levels, which have been done in a number of publications, and then predict levels from basically homogeneous isotropic turbulence, perturbations from that. And so it's really a question of what can be extracted, but also what do you know about your area? In the Baltic, I would not expect there to be any sort of turbulent mixing at that interface, just because there's very little energetics. It's stagnant. That's why it's anoxic. It's one of the reasons. So I think it depends on the region. I think the frequency dependence might help you pull apart, but at the same time, it could be that it's both, right? It's a combination of those types of scattering. And so then that's the next thing to do. That's the postdoc, is to try to be able to pull those things apart and measure them directly. Yeah. Did I answer your question?
John? You say you want ground truth, but that's not obviously the CTD is the one dimension.
Yep.
How on earth would you image centimeter scale roughness?
I do not. I'm not sure. I'm not sure, to be honest. I mean, that's the question: is how could we get at this? And so, I mean, one way you could get at it is through inversion. I think you have to make a lot of assumptions acoustically if you're going to look at the coherent. First, you have to be able to get at the coherent field, and then, of course, is it actually Gaussian distributed? Is it isotropic? Because if you have internal waves that are moving, they have a specific direction, right? And you can create surfaces that have roughness in one direction, but how would you predict that? You'd have to know a lot about the area. So I don't really know how you would get at that. I don't have an answer to that.
I can that we can build microsensors, an array of microsensors.
Like a bunch of microstructure probes,
Three-dimensional array
put
of
them down
microsensors.
together.
What is the scale you're sensitive to in the horizontal?
In the horizontal, well, it depends on the depth, right? So the area insonified would be your sort of horizontal scale. If you have a split aperture system, you have individual quadrants, so you get a little bit more information in the insonified area. But when we were at 13 meters depth, that insonified area had a diameter of 1.8 meters. So
you're really small compared to the internal wavelengths, and you're probably internal waves are much longer.
Yeah, in terms of
than
the
that.
tilts that you would get.
I almost wonder whether you want to take an LES model and simulate through that.
When you say model, to me, it's not ground truth, so.
Right, but to begin to get an idea of what.
Yeah. But I think with microturbulent sensors, you can probably construct something like more in some way that'll sit there in the water column and actually get the fine scale structure of the wave field moving through, both at the long period and at the very high.
Yeah, because there is.
You can do it at a point, but if you put a 3D array of them,
You're going to modify the surface itself. Yeah.
Well,
Depending on where it is.
then we're trying to link them out people and their fiber microsensors.
Also, if you just have a string of them that's high resolution, the water sweeping past, you'll get a pretty good field.
Yeah, and this is, we've been working with some folks at Lincoln that we're building fibers with microsensors embedded in them. So.
No, it's a really good question, and I definitely appreciate the discussion because it's one of those things where you're like, how are you going to get at that measurement? So I saw Gabe put his hand up briefly and then put it down.
maybe if you had like a higher frequency of gas system.
Yeah, actually, now that you say angular dependence, one of the things that we collected in the Kattegat, and I'm not sure how well it turned out, was actually data from a multi-beam, which has very high angular dependence across track. And so certainly I think, the range resolution of a multi-beam, you're not getting down to like a millimeter scale or anything like that, but you could, if you had angular dependence, measure some roughness of the interface, at least in one dimension with a multi-beam, or if you made a star pattern or something, you might be able to actually image that interface. I feel like John maybe has done interface imaging. They certainly look at rough interfaces in a multi-beam. So again, it's a scale question. How small is it getting? It's not really at the scale we're looking for, but it certainly is at least some information. Yeah.
You would be imaging the roughness that we're talking about.
Not this roughness. Yeah.
But you might be able to
Although what is being imaged will be highly impacted by the roughness of the scale.
You probably would be measuring.
Yeah,
There's another way to tease apart your signal.
Yep. Get the slope, hopefully. Juliet, I saw your hand. Yeah.
Couple of things about trying to get at different ways to happen at the same thing. It's really cool because you're getting stratified areas that are really stuff. This isn't where you're gonna get maybe some key or a lot of oceanographic go up and they run at these and they see that great structure, but that's the current going. You're getting places where it's still and it's quiet. And other places where I see people measuring that water structure is with the LiDAR systems. But I'm not sure if anybody's done anything with that still water, unless they're getting the microorganisms scattering with the LiDAR. And I don't know how much you looked at that with what you're doing too.
Yeah.
Like That's a,
Yeah, I
that's
mean,
an interesting space to like. explore.
scattering, yeah, so I think scattering from organisms is definitely, I mean, so first off, scattering from organisms is often associated with stratification structure. So that's one of those components of scattering, the scattering field, that if you're in a region like the Kattegat, you might need to account for. As far as the use of LiDAR or ADCPs, the idea of measuring the currents and looking at two layers in places where they're not stagnant and seeing how quickly they're moving past each other might help you also understand whether or not you would expect to have roughness on the interface. But yeah, I hadn't thought about the use of LiDAR underwater, I guess, doesn't jump to the forefront of my mind.
I want to make sure the committee members that are remote have a chance. I think Andoni has her hand up. Andoni, you should be able to just chime in.
Great, thank you. I actually had a question. I think I missed the first 2 minutes about the structure of the thesis defense and whether you save committee member questions till the closed.
You missed that part. Yeah, no. So what we're gonna do is we'll open the questions to anybody right now, and I'll make sure you and Martin, Christian have a chance to ask questions with the public here. But then we'll dismiss the public in probably another 20 minutes or so, or when the questions run out, and then we'll have a chance ourselves to ask questions, to follow-up questions.
Okay, great, thanks. I'll keep my questions till the closed section then. Thank you.
Okay, it's up to you. Martin?
Yes, can you hear me?
Yes.
Yep.
Okay, good. Okay, I'll keep most of my questions too, but I have one question that I'm a little bit curious about, because Liz, you have said now many times that the Baltic is very stagnant and so forth, and that kind of raises my curiosity a little bit. How stagnant do you think it is, and what do you think happens with the hypoxia or the low oxygen zone over the year? And I also wonder there what your method can help to resolve whatever is happening further.
Yeah, thanks, Martin. That's a good question. Also a clarification. I will just say that there are plenty parts of the Baltic that are not stagnant. There's work by a student at Stockholm University who's been looking at these very large overturnings in parts of the Baltic. So certain parts of the Baltic are stagnant. They tend to be associated with low oxygen zones. And it's kind of a feedback loop. If you don't have a lot of energy, you're not mixing water masses together, you're not oxygenating deep waters. And the Baltic also happens to have a lot of nutrients being pumped into it. There are a lot of river inputs. So you have a lot of primary productivity that's sinking, and then that's being decomposed, and it's pulling down the oxygen. And as far as oxygen conditions over the year, so there are lots of programs in the Baltic that study low oxygen conditions. And I've seen quite a lot of research on the expansion of both hypoxic zones, which are not fully anoxic, not fully no oxygen, but very little oxygen, and then the expansion of full anoxic zones, which there is no oxygen. And I've seen that those are generally growing, and they have been linked to changes in climate and the warming of Baltic surface waters. I'm not sure that I have seen anything specifically about seasonal low oxygen zones, although if I had to just tell you what I would guess, I would say that I feel that you likely would see some kind of seasonality, because often you have phytoplankton blooms in certain months. In the Baltic, I would guess that would be as soon as any ice from the Baltic is gone. And then perhaps when you have a lot of river input in the fall, perhaps, and then you would have a lot of blooms, you'd have a lot of organisms sinking, and then you'd have a drawdown of oxygen after that. So there would be a delayed effect. So that would be my guess in terms of seasonality. As far as my method and looking at seasonal changes in anoxia, I do think it could be possible to track seasonal changes, but it would be very important to collect direct measurements of the oxygen levels, because when we look at the stratification interface, we are not tracking oxygen directly. What we're tracking is that interface between the two water masses. It happens to be coincident with the sort of onset of low oxygen, partially because the stratification is sort of creating this barrier and almost holding the low oxygen water down. It's preventing it being ventilated. But if you had the low oxygen zone expanding beyond that stratification interface, you wouldn't necessarily observe that in the acoustic data. But I think we did a little bit of work in the Bornholm Basin where we tracked the stratification interface, and it was offset from the level of anoxia by a certain number of meters. And that was a very over the region we looked, there was very good correlation there. So we were able to track the low oxygen zone by saying stratification structure is here and X number of meters below is where we see the onset of low oxygen, but it would require ground truthing to check. Does that answer your question?
It was fantastic answer, and that it really was really great. And now I don't need to ask so much later, actually, because
Oh, great. Well, that's
you
perfect.
ticked a whole bunch of my concerns and questions. Great answer.
Christian, do you have a question you want to ask in the public part?
Sure, I'll ask a question. So on your slide here, it says delta Z is smaller than 3.5 centimeters.
Yes, that one. Yes.
Yeah. So, but the thickness of the stratification is something like half a meter, 500. So I'm a little bit confused. I mean, what does that mean?
Oh, so when you say thickness, are you meaning what we're measuring from the CTD, what we're seeing there?
The base of the mixed layer is what you're tracking, right?
Yes.
Here it looks like something like half a meter, the thickness of that sort of part of the halicline.
Well, so what we're tracking here, so in the Kattegat, there's a surface relatively mixed layer, and then there's this interface, and then there's a deeper water mass, and then as you can maybe see, there's some other stuff happening deeper than that. And so at the interface between the surface mixed layer and this deeper water mass, there's a stratification interface. And what I'm saying is that the true vertical extent of the transition between those layers is something like 3.5 centimeters predicted from this model, predicted from the frequency dependence. And so what you would see in a CTD cast, for example, would be a measurement of both, temperature and salinity, and you'd also get pressure. But the CTD, is transiting down with a certain downcast speed. Maybe I think here was something like maybe 30 to 40 centimeters a second. So you're getting a number of samples, and then the temperature salinity probes have a time constant, so they can provide you data at a certain frequency. And so what I'm saying is, while they could be used to constrain the vertical extent to less than a certain amount, the true extent of the interface is actually much sharper. It's not captured in the CTD. Now, that's part of the reason we'd like to go out with a very high resolution system and actually measure that interface, basically constrain it at these kinds of measurements, because it's hard to say whether or not that's the case. Although I would argue that especially for salinity measurements with the CTD, you have an intake valve on the bottom, and then you're pumping water in and measuring salinity. So you're not measuring it right there at the water. There's a delay in that measurement. Does that answer the question, Christian?
Yeah, I guess so. I mean, so basically you're saying that there is structure within this sort of sharp transition, and you actually measure that sort of very high resolution sort of wiggles within the halicline.
Yeah.
I mean, but then if you go to the Gotland Basin, you have this very, very clean, nice. We also resolved this halicline very nicely, I think. We were binning to 2 decimeters or something. It's low energy, and you come up with 1.8 centimeters.
Correct.
And it's 1 meter well resolved, nicely behaved interface.
Well, I mean,
it's a bit shocking, I think.
I would argue that I'm not disagreeing that you are certainly the Baltic. We certainly can put the CTD down slower, but you just said that you were binning the data at a decimeter, which is correct me if I'm wrong here, but that's 10 centimeters. So certainly you're saying, okay, the interface could be at this level, but it could also be sharper than that, right? The whole point is that if you have higher resolution data, you could potentially infer something a lot sharper. I mean, I think we'd have to have a look at the data, and maybe we could have a discussion about it. But my argument is that the acoustics can give you the actual sharpness measurement, at least at the scale. The acoustic data is higher resolution than what the CTD can predict. And so the sharpness that we can measure is closer to the true sharpness of the interface. But again, this is the inversion of the model, and I don't have a direct measurement of this interface vertical extent. So I certainly, before hanging my hat on it, would want to have very high resolution measurements that say, no, we definitely can resolve this, and it is definitely, say, a 10 centimeter vertical extent, or no, it's smaller than that, and that would give us a sense of as whether or not all of the model and every assumption that went into this model isn't throwing us off.
Yeah. Okay. So that's good. I'm happy with that answer, and I think we can provide microstructure profiler data that.
Oh, well, that's exactly what I want.
Yeah.
Kristen. Wonderful.
Oh, we have plenty, right? So yeah, nice. Thanks.
I was just gonna suggest that maybe we should all pitch in and get this.
Exactly.
They're $75,000.
I have a question related to,
$75,000 if you got that
You're
hanging around.
I have a question related, I'm sure that's how you'd want to spend.
Oh, 100%. That's how it's going. Sorry, Sam.
I had a question related to, so you're looking at the Kattegat.
Yes.
You're saying that there's an influence due to surface roughness, that, as Jamie pointed out earlier, the scale of the internal waves that you can resolve actually.
Yep.
Data directly. You know, there are a few tens of meters or something like that. What are there models for what that roughness should look like? You're using a Gaussian spectrum of roughness.
Yeah.
Is there have people looked at that?
I haven't seen any models. I wouldn't have said that I've done a thorough literature search. I do think if we have propagating internal waves, which we do have, and we have a tilting of this surface, they're big. They're the ones that we're resolving are wavelengths of something between like 12 to 20 meters. They're pretty short wavelength internal waves. They're certainly causing tilt. So if we really wanted to model this interface very much correctly, we'd take our interface and we'd also give it the distribution of tilts with roughness on it, or not roughness.
I think
Your roughness is down.
I think Tom's asking,
Well,
is a fine scale roughness
but-
on top superimposed on it.
Sometimes, but sometimes the roughness in the way that we model is we take that correlation length and we stretch it really long. So then our roughness effectively becomes just tilt of the surface. And I'm just saying you could have tilt with small scale roughness. I don't know if there are models. I imagine that must be something that people have thought about either in the, no, Jamie's shaking his head, but in the atmosphere, maybe thinking about because there's other regions that are stratified.
For surface gravity.
Yeah.
Yeah, I can't imagine, given the mechanism that internal wave generated, that it would generate a small field.
Right.
In that there's shear of some sort, that you're gonna have to have some kind of.
There's no John Swap model for
Right.
internal waves.
Yeah.
So it's really, we got a lot of postdocs.
Yeah, so I would say that that's exactly the kind of thing that we could utilize if we're not sure how to get at direct measurements, or direct measurements are causing, we're struggling to get direct measurements. If there was a model that helped us predict, if we could say, all right, I can tell you what the long period internal wave is of this, and if this is how fast it's moving, can we then predict what kind of small scale structure we might have? I would say that's what we're looking for. I don't know if that exists though. I certainly haven't done a literature search.
And the density, so I think it's interesting.
But you do think it's there?
I think it could be. I hope it is. That would be nice.
Can I show you slide 17?
Sure.
Just a curiosity.
No, that's fine.
So I'm curious about, so that was the interface check, but you see there's a deeper layer that,
There is right here, yep.
that rises very quickly.
Rises up, yeah, rises very quickly.
Is the assumption that's biological?
I would have to have a look at the data, to be
Because
honest.
what I'm curious about is if you could separate out, look at the scattering coming from the area that doesn't seem to have that biological component from one that has it, see if you see some frequency dependence that's quite different.
I could certainly have a look at the CTD cast. We are diving here into much deeper water, so we're coming into basically a trough. So it's possible also that that's some kind of oceanography that's being modified by currents that are coming through here potentially. I'm not certain what it is, but certainly, yeah, you could look at the frequency dependence of this region. It certainly is scattering sound much differently than our very discrete stratification interfaces, a sort of region of, sort of elevated scattering. It's very speckly, so there's a lot of variability in it. So yeah, that certainly could be biology. We also had a camera on this CTD, so we could have had a look and see if we see any, congregations of biology at 78 meters depth. That would be possible.
Can you get one last one?
Yeah, well, just quickly to reinforce your intuition on the vertical resolution of the drop CTD, which is pumped. It's meters. That's what microstructure is for. Not meters, but 8 meter.
Yeah, meter or decimeters.
Have you ever thought about what data you need to gather to invert your stratification to get a picture of the density field?
Oh, I haven't
That's
thought
what
about that. Yeah, I haven't thought about that. I think, sound speed and density are very closely tied together. So I do think that that should be possible. I mean, to get out a direct measurement of the density field, you'd have to have some kind of direct measurement to pin everything else to. If you were saying, all right, well, I know there's an interface here. I know that the change, say you could go from, here's your wave number perturbation, here's the change here, to a change in density, you then need to pin that to some known density level. I imagine that would be possible. I haven't thought specifically about that
How
application.
blind are you to weak stratification that could add
Well,
up to?
It depends
lot
on the frequency.
But didn't your model ignore the density gradient term?
It did not ignore the density gradient term.
So it's insignificant.
It ignored the density perturbation gradient term, which is a small term, which was insignificant, but in the wave number term, that is a function of density. So density is still in there. It's not that we're saying that density itself is insignificant. It's just that term is not important compared to the wave number term. But no, Jamie, I haven't specifically thought about that. And I think for oceanography applications, those are the kinds of comments that are helpful, because I think a lot of time in the world of water column acoustics and what do I care about? And I care about density, but I often care about it in its relation to sound speed. And can I just think about sound speed? So if oceanographers are saying density is what I care about, then that's helpful for, the broader impacts kind of statement. This is why we need this information. Yeah.
Just a comment, there's an interesting related question about what the lower limit on your actual measurement is. Like, is that all that black stuff? I think that's what you're. Stuff in there that's going to add up to a lot of you anyway over the whole thing. The related question is like, how much further can we push the noise floor? Is that what is it those density gradients that fundamentally limit?
But this really ties into the whole initial question: is what kind of change? What's the nature of that change that we see? That's really the fundamental question. Okay, well, let me thank you all. Let's thank Liz again for a